Thanks, Michael. How's everybody doing? Lunch was okay? All right, that's good, that's good. Is this not the best conference? This is like the best conference. It's like, right? It's like the best people, the best size, the best topics. It's just awesome. So I'm sorry that you have to experience this next hour, which will be my attempt at a keynote talk. I had a keynote talk all lined up, and then I found out that Leslie was going to be here, and she had already heard that talk. I'm like, I can't let Leslie know that I only have one talk. I have to make a second talk. So this is my second replacement talk, and I guess if you don't like it, you could blame Leslie, but you probably should blame me. So, all right, so what I want to talk about is efficient reinforcement learning and AI with a focus on this notion of interaction and teaching. So if you read the news, and you kind of have to, it sounds like maybe reinforcement learning and all of AI is solved at this point, right? There's you know, deep reinforcement learning is winning in all these really complex games that it scares people. I just read a book, actually, about national security, where the Joint Chiefs of Staff got a demo of the DeepMind Atari stuff, the DQN stuff, back in the day when that was just brand new, and they all left the room like, we have to change the way we're doing defense, right? So this has had a huge impact on people's thinking in the world, right? Not just us. Reinforcement learning has become a key technology in robotics. It's, you know, general purpose AI chatbots are trained using various kinds of reinforcement learning setups. This is kind of a big deal. And again, if you read it in the news, it sounds like, well, this is done. Why are you people still working on this? And I'm like, well, first of all these examples have their weirdnesses, right? So the strategy that did so well in Go, it has these weird quirks in it that actually you can trick it. You can actually have an amateur beat it consistently. At least one version that's been studied closely. The Atari strategies. Well, I was just going to say that there was all these results with chatbots being trained with reinforcement learning and learning to become great reasoners. But then there's these follow-up papers that say things like, hey, they're just as good reasoners if you randomize the reward function. I'm like, then the thing that's happening is probably not what's actually, the thing that you think is happening is probably not what's actually happening, right? If you can actually train it on random rewards and it's just as smart, then maybe reinforcement learning wasn't what was actually doing it. People talk about how, well, we can just make these systems better if we just keep growing the data. They keep doubling the size of the data that they use to train these. And at some point, you're actually outpacing the availability of like human output. So what we need, I think, are systems that we can trust to do what they're actually built for. And this is something that is a shortcoming with a lot of these systems, that they do some things really well, but then sometimes they do other things really badly, and then we can't really have our faith in them. So what I'd like to do is focus on algorithms that achieve near optimal policies, so that we actually know, hey, this algorithm in this kind of environment is actually going to do well by some definition of doing well. So I'm going to talk about a couple different versions of the problem. We'll walk through these, but I'm going to start off with the kind of classic interactive setting. So what do I mean by the interactive setting? So we've got some kind of decision process. We've got states and actions and transitions and rewards and discount factor, satrig, I guess. And a learner is interacting with the environment, issuing actions, observing states and rewards, and it's basically collecting data, and the data is in terms of these little SARs transitions. And so the learner then is going to use that information to generate a policy pie, and we're really interested in policies that achieve optimal reward, and in particular, how much experience, how much interaction, how big does this D have to be so that we know that it's going to have near optimal rewards, that it's actually going to do the thing that it was built to do. So I'm going to look at two different settings. One is the tabular setting, where we understand things pretty well, where the number of states is just some measure of the complexity of the system. But also, I'm going to look at the compact setting, where now it's the size of the transition function that is kind of our main parameter. The number of states might be exponential in that. All right. So let's just kind of dive in. So this should be review in the sense that these are older papers, 2002. But one of the ways that we can actually guarantee near optimal behavior in the kind of classical tabular reinforcement learning setting is to have the learner build a model of the transitions that it experiences. It actually builds the transition model, and then it can use that to make decisions with respect to its reward function. So one of the ways that this can be made to work is by having the learner actively seek out states to learn about. So it doesn't just wander around, doesn't try to do a thing. It's actually trying to figure out where haven't I been yet so I can learn about those so that I can actually make decisions and be nearly optimal. So the first paper that was able to do this was Kearns and Singh in 2002. This was the E-cubed algorithm, or explicit explore exploit. And it was really kind of a breakthrough because up to this point, we had algorithms that could, in the limit, converge to near optimal behavior, but we didn't have any ability to say, actually, with a reasonable amount of interaction with the environment, we can achieve near optimal reward. And they had an algorithm that had an explicit mode for exploring and an explicit mode for exploiting. Around the same time, shortly after, Brofman and Tenenholtz proposed an algorithm that they called RMAX. And one of the nice things about RMAX is it really just works by assuming that states that you don't know about must have really great reward. And so just assume that if it's unknown, it's good, because how could that possibly get you into trouble? And what that does that's neat is it makes exploration an automatic thing. So as long as the system thinks that there are states that it can reach that have impact on its value, it can actually plan to get to them, to achieve those states, and then maybe when it gets there, it learns, oh, that wasn't actually as exciting as I thought, but it's updated its model, and you could show that the number of times that it needs to actually do that kind of update is small. It's a polynomial in various kinds of quantities. So that seems like it's a really nice kind of setup. One of the reasons that this is hard, in case it doesn't seem hard to you, but if it's not obvious why it would be hard, are things like this so-called combination lock environment that says we've got a series of states that are arranged in a chain. There are actions that can actually move you down the chain towards this purple state, which gets you a high reward of 20 in this case. But any other action that you take resets you to the beginning. And so if you have some kind of exploration strategy that has randomness in it, what you find is that the agent kind of walks up the chain and then does something random and then resets to the beginning and then does it again. And so, right, so after, it really can take a very, very long time before it ever even experiences that last state. And in fact, that time is exponential, right? So it really can take too long for it to explore that way. And so, yeah, the assumption is if it's a state you don't know about, think of it as good, draws you out there, get high reward. And so when you actually run this kind of algorithm, in this case, a simple grid world, this is the kind of behavior that you see. The agent, instead of just being random, it's sort of scrubbing itself against all the different parts of the grid, right? It's like getting to know all the nooks and crannies, occasionally falling into the goal, but that's okay. Everything that it doesn't see or hasn't experienced yet, it thinks is maybe as good as the goal, until basically it's seeing everything that is relevant, and then you see the behavior that it starts to take at that point is more and more directed towards just getting to the goal. Bang, bang, bang. And it learns potentially multiple optimal policies of the goal. It gets this environment really well. So that's terrific. I think it's very nice. It would be nice if that was all there was in the world, grid worlds, because we'd have that totally under control. Some of the key ideas that make this work are things like the simulation lemma that says that if you have an agent that's optimal in an approximate model, it's actually approximately optimal in the real world, in the environment. The explore-exploit lemma says that if you can't reach unknown states quickly, then you're nearly optimal, or you know everything you need to be nearly optimal. There's this notion of bounded learning time that says if you can reach unknown states quickly, learning will progress significantly. Each time you visit a state, each time the agent visits a state that it hasn't seen enough, it's going to learn something valuable. And so that's only going to happen a small number of times before it knows everything it needs to know. So if you put all these pieces together, you can actually construct a polynomial bound on the size of that data set before the policy that's learned is near optimal. So that's great. So we can start to fill in our table. We've got one sort of piece of good news in the upper left-hand corner. What if we now start thinking about these compact environments? So a compact environment is one where the transition function may be represented in a way that can cover an exponential number of states with a very small description. And so if you just literally take these results and port them over to the compact setting, then you get algorithms that take exponential time because there is an exponential number of states, and these algorithms scale with the number of states. So that's not great. But there are exceptions to this, so I put a little asterisk, and I want to tell you about the exceptions because I think they're helpful to know about. So there are situations where we can actually learn that transition function efficiently. So even though there's many, many states, the transition function itself is compactly represented, and we can learn basically in time proportional to the size of that representation. So when can we do this? So transition function, you can think of it as a mapping from state in action to next state, And let's say that the learner knows that the transition function comes from some hypothesis class, some set of possible transition functions. And it could be a very big set, or it could be like 3 different possibilities, whatever it is, but it has that sense of what that set is. If that set H has special structure, then learning can be efficient. And so what do we know about that? Well, first of all, a useful thing, what we're going to try to leverage is the notion that in the RMAX algorithm, we're going to apply ideas from the RMAX algorithm. The main idea is that the learner needs to know when a transition outcome is known or unknown. If it's something that can predict from experience it's already had, it's known. If it can't be predicted, it's unknown. And each time an unknown transition is taken, we have to make significant progress towards learning that transition function. So if we could just distinguish what we know from what we don't know with respect to that transition function, or if we had an algorithm that knows what it knows, which I called KWIK, then that would be a really useful tool in the context of RMAX to be able to learn efficiently in the size of that representation as opposed to the size of the state space. So if you haven't seen KWIK before, and maybe you haven't because you're not citing it very often, so let me help you with this a little bit because you're gonna want to use this. It's good stuff. So here's a cute concrete example. So we're just going to learn a function now. This is not the RL setting. We're trying to learn a function f of x. So x takes in an input, and it just produces yes or no. And the function comes from a particular class. And the class is, there's some unknown natural number k, less than or equal to 1,000. If x is divisible by that k that we don't know before we started learning, then the answer is yes. And if it's not divisible by k, then the answer is no. OK? So far, so good? All right. So in standard like pack learning, where we're just, or distribution sensitive learning, what we're going to do is look at a bunch of examples of number and output, and then we're going to try to infer from that what the correct generalization is. But in the KWIK setting, it's a little bit different. It's going to be an interactive game. All right. So here's the interactive game. I'm going to tell you the input, 6, and you're going to tell me the answer. But if you don't know the answer, you can just say, I don't know. All right. So 6? I don't know either. Yeah, that's a good point. All right, so the prediction you should say is I don't know, IDK. And now we actually get to find out what the function is for that. And the answer is yes. Okay, so now you know some things, not everything, but you know a little bit. You know that whatever that k is, 6 is divisible by it. All right, so now you should be doing quick little like, what's the prime factors of 6 kind of thing. But that's useful information. So now I say 20. Really? Okay, no, I guess that's right. You don't. But the answer is no. All right, so this k that you don't know, x is 20 is not divisible by it, but 6 is. All right, that narrows things down a little bit, right? So now I give you another thing, 24. But you know what k is? You do not know what k is. But you don't have to know what k is to get this answer right? Because the information that you have to this point doesn't completely restrict what you have, but it disambiguates the answer to this. So you can say yes without even having to ask the function. So that's great. So that didn't cost us. We're gonna pay with respect to the number of I don't knows that we issue. So it's great that we got that one. All right. What about 25? And that's a no. So even though still you don't know k, you know enough to know that 25 isn't going to work. All right, and finally I say 15. You don't know. You shouldn't know. Actually, maybe yes, you know because you saw the slides in advance. But if the information that I gave you is insufficient to get the answer in this case, so you should say I don't know. And I say no, and now do you know k? Yeah, and it's 6. Okay, great. Because it could have been 3 a minute ago, but then if it were 3, then 15, it would have been divisible, and so, okay. All right, so this is the gist of this kind of whole quick learning thing. And why it's useful is that we're not depending on the distribution with which I'm giving you these examples. Right? I don't have to sample them in a certain way, and then you don't have to kind of make up some kind of story that only works with respect to that distribution. We're actually getting at the truth of the matter, but we're willing to, or we're going to track the uncertainty as we move through this learning process. All right, so when we implement that sort of idea in, say, an Atari video game, what we find is, again, this exploration, kind of like in the grid world that I showed you, the exploration is interesting. And in this case, it's very systematic, and it's systematic in a way that I think is very human-like, right? So it's not trying to get to all the states. It's trying to get to all the interesting interaction points between the objects on the screen and between the objects on the screen. It doesn't know what the player is, But we see this and it's like, yeah, the player's going to check out the wall, it's going to check out the ladder, it's going to try jumping against the wall, it's going to try all the different things, but like it doesn't have to try it in every, like it doesn't have to try jumping in every place on the space because there's nothing interestingly different there. I gave it a hypothesis class, to be clear. All right, and so now it's interacting with the log and it like rubs up against the log a little bit, sort of getting a feel for how that works. And then once it's done that, it now has all the information it needs to do a shortest path right across the grid. So that's fun, and then we programmed it to do a little happy dance at the end. All right, great. So, so this is really cool. So if it is the case that we know magically that the transition function lives in a particular space, and it happens to be a space where there's a quick algorithm for being able to do the learning, then we don't have to take exponential time. We can actually do it in polynomial time. So that's why I put the little asterisk there. All right, so one of the things that is unsatisfying about this, of course, is that we have to have the right hypothesis class. So if that hypothesis class that we picked is actually too small and it doesn't include the right answer, learning's going to fail. And if it's too big, then we're going to get these learners that are just going to flail. They're going to like rub up against every possible thing in all possible ways. It's going to take forever. So maybe this isn't the best way to build an agent. But before we kind of address that issue, I would like to talk about learning from static data or batch reinforcement learning. So here, some teacher is going to collect data, and that data is going to be supplied to the learner. The learner is going to try to do well based on that. And like part of the reason that I was inspired to think about this in the first place is because there's so much work out there now where they're training up, people are training up chatbots from static data, right? It's just a collection of data. There's no interacting with the real world. There's just what people have said and then written down and then recorded. So I don't know, I feel like as a reinforcement learning person, I'm very offended by this, that this should not work, because you have to interact with the environment to be able to do things. And yet people are saying, oh, these chatbots that predict the next word, they're really agents. They actually can solve problems. They can reason. They can do it. Like, I don't see how that could possibly be. So let's think a little bit about, well, what do we know about learning from static data? So here's the setting. Again, we have I'm going to say a Markov decision process with states, actions, transitions, rewards. And what we're going to get is some teacher policy pi sub d that's going to run out into this environment and collect data for us. And the data is going to be of the form state, action, next state, and so on. A bunch of state, action, next state triples. The learner is then going to get this pile of data d and be told, here's your reward function, and now has to generate a policy, and that policy should be near optimal. How much data is it going to take for that policy to become near optimal? So that's the question that we're posing. And what we're going to look at is different scenarios of what does the teacher know about the transition function and the reward function. Okay. All right, so start off with the teacher knows everything. The teacher knows the whole MDP, the transitions, the rewards, gamma, everything that could be relevant, states and actions. So in that case, the teacher can actually compute the optimal policy, in the tabular setting anyway. And so we have this optimal policy in hand. And now that could be used to collect data. We can actually just put the optimal policy into the environment and let it collect lots and lots of data. It's just data of it doing the right thing. And that data is going to be sufficient for the learner because we can actually present to the learner the data, and the learner can just memorize the action choices in the states that were visited. Or could actually build a model from the states that were visited and then try to plan in that model. But probably it hasn't seen any of the other action choices, so it probably should just stick to what it's seen. So in that scenario, we can actually build a bound B that is polynomial in the standard quantities so that learned policy pi is near optimal with high probability. And the essence of the idea is that if you think about any state in the environment that could possibly have significant value impact with respect to that optimal policy, it's going to get visited by this sample that we run, if the sample is moderately big, and therefore appear in the data, and therefore the learner will know what to do in those states. So it's a pretty easy case, right? It just basically has to memorize what the teacher's data generation process does. All right, so let's move on to nothing's known. The teacher doesn't know the transitions. The teacher doesn't know the rewards. Well, this is kind of hard. And you can't really do any better than exponential. And the reason for that is the teacher, not knowing the transitions and rewards, is going to have to issue a data collection policy that has some randomness in it, right? Because any deterministic policy, there's some environment that's going to cause that to just get stuck. So it has to be random in order to reach the states and learn about what's relevant in the environment. And so again, back to the combination lock, any kind of randomized policy in the combination lock is going to need exponential steps to actually reach the important big reward at the end of the chain. And so there really is no way to get around that because the teacher doesn't know what the environment is. Anything the teacher chooses, there's some environment that's going to thwart it. So it's, we're stuck in that case. That is kind of a cruel case. So you know nothing about the world. Now give me data that's going to help me optimize. All right, so here's an in-between version that I think is really interesting. Let me see what I have in terms of time. All right, I will kind of go through this in a sketchy way, but I thought this was cute, and I hadn't seen it in the literature. So the question is this: the teacher knows the transition function, doesn't know the reward function. So what the teacher's trying to do now is to figure out how to act in the world so that the data that's gathered from acting in the world is going to be sufficient when given to a learner to optimize any reward function that could be, or nearly optimize any reward function that could be relevant. Okay? So how might we do that? Well, the idea is that given the transition function, there's right. So we're only going to, first of all, we only care about states that can be reached by some policy with high probability. There could be states in the environment that are just really, really hard to get to. They're not going to have significant impact on the optimal behavior, no matter what the reward function is. So we can just kind of pretend they don't exist. That's fine. So the idea is that we're going to build a collection of policies, one for each of the states in the environment that can be reached with high probability, that is really good at just getting to that state. Like, that's its job. The policy's job is like, I want to get to that state, I got to that state, yes! And then dances on that state. All right. If it can. If it can't, it might get reset and have to get back to that state. So we have a collection of policies for all the visitable states, and then we go through a process to translate that into a single stationary policy that actually has very similar behavior to all of those policies. So basically, we've created a kind of Markovian exploration that just isn't going to get stuck. It's actually going to explore that space sufficiently. And we got this result by modifying some known results from graph theory. This was a problem that I posed in a talk at Yishai Mansour and David McAllister's Festschrifts. And I was like, I think this is probably solvable. And then we all sat down at lunch and we all worked it out unsuccessfully. And then Yishai sent us email the next day saying, here's the solution. So 2023 lunch, that's the citation. So the idea is basically what I said, is that we create a bunch of different policies, and we can do that easily by just saying, let's create a policy for a state by just giving that state +1 reward and no rewards elsewhere, optimize that policy. Then we can start merging these policies together by saying, anyway, we compute a bunch of, so the thing that makes this hard, and the reason that this is at all tricky and we didn't solve it during lunch, is that the issue is that if you have very different policies for getting to very different states, and you just randomly kind of blend them together, then you can end up with an agent that just flails. Like, it's not good at getting to any state because it keeps interrupting itself and then randomly choosing some other policy to follow, and then and it just never really does what it's supposed to do. And so the trick here is to come up with the right way of normalizing the probabilities at each state so that it doesn't waste time in states that it's already likely to have visited. And so we compute how often the different states are visited by the different policies, and then we divide by that. We basically normalize by how often that state was being visited anyway. So anyway, we put the construction together, and at the end of the day, we can, again, create this bound B on the number of steps that's polynomial and the standard quantities, that if we run this policy for that amount of time, it will have covered all the reachable states with high probability. And so you could learn whatever reward, any policy that you want from that. So I think that's sort of cute. So that's great. We fill in a couple more things with polynomials and another one with an exponential. But again, we kind of really care about the compact case. As fun as it is to think about the tabular case, the world is more complicated than that. So what happens if you just take these results and port them over? Well, everything gets exponentially worse because there's an exponential increase in the number of states. So first one becomes exponential, second one becomes exponential, the third one becomes doubly exponential. So this is not ideal. And the thing that I think is really interesting about this is even hard in the fully known MDP case, right? So the teacher knows the right answer and still can't manage to explore in a way that actually conveys that to the learner. And why is that the case? Well, I mean, if you just think of this in a straightforward way, well, sure, there's an exponential number of states, but that doesn't prove that you can't do it if maybe there's a clever way of actually doing it. The reason that it really does take exponential time is because you can encode in a compact transition function basically an exponential number of combination locks. And so during any kind of polynomial data sample, it's only going to visit a handful of those combination locks, And so when it's done collecting that static data and then it gets to interact, it's going to walk and with very high probability end up in some place that it's never seen before, and it's not going to know what to do there. So the policy is not going to be near optimal. If you turn on learning and let it continue to learn after that fact, it can fix that eventually. But I think it's interesting that the theory sort of turns out this way because there's a couple really nice empirical results from the literature that have very much kind of tripped on that issue. One that I find particularly compelling is this paper by Ostrovsky et al. From 2021, where they looked at what happens if you take a deep reinforcement learner and you put it in an Atari game and you tether it to another deep reinforcement learner. So one is actually doing, I think it was DQN, so just learning about that environment, learning how to optimize, and the other one is just seeing the transitions that the first one has generated. Right? So they're both seeing exactly the same transitions. Right? The first one is making decisions and seeing the transitions. The second one is just passively being dragged along, but it's seeing the same data, right? So it's really the same problem. But if they're initialized differently, what you find that happens is take the tethered policy when you're done learning, the first one has gotten near optimal, give the second one the opportunity to start acting in the world, and it's terrible. Right? It's not good at all. And the reason that it's not good at all is because it never got to find out the things that it thought were good are not actually good. The first agent, the agent it was tethered to, did. Anything that it thought was great, it actually went and said, oh, this is great. No, that's not great. And it learned not to do that. But the second agent, the tethered agent, doesn't get that kind of experience. So it ends up actually being quite poor. And the way to fix this, of course, is, well, you have to let it interact with the environment so that it can actually learn. Another paper that was, I guess, a decade before that from Ross, Gordon, and Bagnell, the paper that introduced the algorithm Dagger, I thought was really interesting too, because there the idea is we're doing apprenticeship learning, so we have an agent, an environment, and we walk it through the way that we want it to behave, and it has to learn that. So it really is, it's like learning from that static data generated by the person. And even if it learns it ideally perfectly, what you find is that there's just too many ways that policy, that learn policy, can fail. If it's in a big enough kind of state space, bad things are going to happen. It's going to fall off its known policy, and then typically, in the video that's associated with the paper, it then falls off the edge of the earth, because they were doing it in some kind of video game where there was a raised track, and then it would just drive, and it would just completely fall off. So it was very sad. And the way that they end up fixing it in the Dagger paper is by saying, well, we're going to have a teacher kind of intervene. If the learner starts getting into parts of the state space that it just doesn't know what to do in, then we're going to add more data to its data set. We're going to let a person kind of steer it back on track. And so what it learns then is, instead of just like this very thin policy that can work through the state space, it learns a much kind of fatter, thicker policy that is able to not just execute well, but executes well even with deviations to the path that it's taking. So I think that's really neat, and it sort of fits with this notion of learning from static data is really hard, if not basically impossible. In the worst case. I'm not saying that if you've done this, you didn't do it. You probably did, but it's not a general algorithm that we can actually depend on and know that the learners are doing what they're supposed to do. All right, so what I want to do next, this is kind of now building up to the punchline, is introduce an alternative learning model that a student and I explored that we called Impact. But it's really for this case of let's take this teacher thing seriously. Instead of the kind of classic machine learning scenario where it's like, we give you data and you give us back smart answers. Instead, it's more collaborative, and we allow for the possibility that somebody needs to guide you. Like, as smart as we all are, like if we were just left at birth on a desert island, we probably wouldn't do so well. Like we got hints from the rest of society. So let's come up with a formal model of that and see if that maybe gives us some ideas about what we could do in the learning setting. All right, so think of the hypothesis class of transition functions as being vast now. So instead of like a limited case, it's sort of anything that you can express. And the state space can also be exponential. But now, instead of learning all at once, we're going to have a teacher provide a kind of curriculum. We're going to let the teacher present the data in a particular way. We're going to let the learner learn a little bit, and then we're going to iterate that kind of interaction. So in each phase of learning, the learner is going to consider simple combinations of its existing knowledge. So this, I think, is a really, really core idea that we haven't squeezed for all it's worth. And the notion here is that you can make learning really easy if the learner is never asked to do anything that's much more complicated than what it has already done. right? So that's different than just saying, well, learning is really easy if you only have to learn really simple things. Like, no, you can learn complicated things, but you have to build up to it, right? You have to say, here's a simple thing, but this is a little bit outside what you've learned. Learn that. Okay, now that you know that, you can use that in learning the next complicated thing. And so for me, it's kind of like a well-designed video game. Like, I don't know if you've ever played Portal, but like I felt like that was what was happening to me when I was playing Portal. It's like, I don't understand how I'm going to move through space and time. This is very weird. But then all the levels kind of got me like the next little bit of knowledge that I needed. And by the end, I was doing things that the beginning me would have thought were absolutely impossible. And so that's why I want to sort of capture that idea in the learning setting, is that, what can we do to actually walk a learner through increasing levels of complexity until it can do something basically arbitrarily complex. All right, so the way we do this in this work is we extend the PAC learning framework to learn functions, as I said, of arbitrary complexity, and we called it iteratively moderated PAC teaching, or impact. I mean, clearly this is one of the cases where first we came up with the name, then we came up with the algorithm, because you gotta prioritize. All right, so high impact research. All right, so, and I came up with it quick. No, that was a different project, sorry. All right, so the essence of this idea is we're gonna limit the teacher and the learner in very particular ways. So obviously, if we have an all-powerful teacher, we just say, oh, the teacher can do anything. The teacher knows the problem, the teacher knows everything. Then the teacher could just output a program and the learner could just run the program and doesn't have to learn. There's really, that's like too much. So we have to limit that channel between the teacher and the learner. And so the way we do this is the impact teacher, and again, this is in the supervised setting. So there's a data source that we can draw from, and then there's like labeled examples that can be presented to the learner. So here's what we're going to do. The impact teacher knows a representation of the target function. So the teacher knows an answer, knows a representation of the answer. And it can sample from the environment distribution to get training examples. And it can present them to the learner, but it can hide confusing examples, right? So the teacher has a thing that the teacher can do, which is like, you're not ready for this instance yet, right? So instead of presenting all the data all at once, teacher, kindergartner, calculus sort of thing, we're going to say, hey, there's other stuff out there. You'll need to know about it later. But for now, just really pay attention to, like your Greek letters. We'll get to calculus soon. All right, so that's the moderation part of the M in impact, is about this notion of being able to elide some of the data examples, not present everything to the learner. And the other thing the teacher can do is signal the end of a round of teaching, right? So the teacher can think for a little while, sample a bunch of data, look at that data, throw out some examples that it deems like not appropriate for right now, present those to the learner learns, and then the teacher says, good job, you've learned that lesson, all right? And then we're going to repeat that process. All right, so I'm going to walk you through an example of this, which maybe I shouldn't, but I felt like the description at this point is still very high level and vague. I just wanted to kind of, peel back the curtain a little bit and give you a sense of how this looks. So here's the function that the teacher knows that the learner is going to need to learn. It's XNOR. It's an exclusive NOR of 3 variables, and it's ignoring the third variable. So it's x1, x2. They're going to get ORed together and ANDed together, and then the OR is going to get NOTed. Basically, this is equivalent. It's like basically the answer is yes if x1 and x2 are the same, and no if they're not. Okay? So that's what we're trying to teach. Obviously, we have learning algorithms that would be fine at this now. This is a small example. But there was a day in the history of machine learning when equiv was not learnable because it's not linearly separable. So it's a little hard, but yes, I know it's simple. All right, so here's what the teacher's going to do. The teacher's going to sample a bunch of examples from the environment saying, okay, x1 is 0, x2 is 1, x3 is 0. What's the label for that? It's 0. The teacher is not picking those examples. The teacher's just sampling from whatever the data distribution is, but the label is the true label. Okay, so it collects that data set. And then it decides, okay, first thing I'm going to do is teach the learner gate 1, which is the OR gate at the bottom there. And so to do that, the teacher is going to mark which things in the data set are consistent with that particular gate. Okay? So basically, even though the Y column is the full function, sometimes it actually lines up with the OR of the first 2. Sometimes it doesn't. And you'd think, well, that's sort of random that it does and it doesn't. And it's like the answer is yes, but there's only 2 bits. So either the OR gate or its opposite is going to have plenty of data. Right? So again, we're going to teach it a function that that the data is not really designed to show, but that's okay because the teacher is going to be sneaky, tricky. Okay. So so what the teacher realizes is that we can teach the negation of the OR gate with 4 out of the 5 examples that are in the data set, because they all have the property that the y is really just the negation of the OR of x1 and x2. So we present that, the teacher presents that to the learner. Ooh, did we lose something? Just wait. And we're back. All right. Great. So, give that to the learner. The learner's going to learn some very, very simple function of just 2 variables in there where you can predict the output. And the teacher was hoping that the learner would learn the OR of x1 and x2, but it doesn't actually. It learns the NOR of x1 and x2. It actually learns the output of gate 3. It's okay. It's fine. But it's not exactly what the teacher wanted. But we're not going to care. We're just going to say, that's great. You learned something about the data that we really needed you to know. And so the teacher says, that's the end of this round. The learner internally says, OK, I'm going to learn that lesson and call it W1. Right? So basically take the data set, and we're going to augment it with a W1 column, as if there's a new input. The input is exactly what it learned in the previous round, but now it's sort of taken as a given. It's a primitive, if you will. All right? And then we're going to repeat this. We're going to say, OK, the teacher is now going to try to teach gate 2 using that data set. It turns out that the first, third, fourth, and fifth rows are consistent with the AND of x1 and x2. So it elides the second row, presents that to the learner. In this case, it actually learns AND, which is great. Then we do it again to teach the third gate. And it turns out that it didn't really need to learn that because it had already learned it. So it just learns to copy the value that it had. And then again, each time that it learns something, that's getting added, the data set's getting extended widthwise. And now we ask it to learn the full function. And it's easy, because it's just now an OR of 2 of the things that it's already learned. So even though it had this complicated, not so complicated, slightly complicated nonlinear function that it had to learn, all the pieces were just there. So it learned a very, very simple combination of them to get the final function. So the learner ended up learning a slightly different function than the teacher was teaching, but it actually gets the right answer. So it learned what it needed to learn. All right, so that's kind of impact in a nutshell. Some observations about it. The teacher has a compact representation. The teacher is conveying lessons kind of bottom up in that representation. It can always use the data distribution to create a data set that something really useful can be learned from. The learner is always learning just simple binary logic gates. Very, very simple. If it learns a wrong gate, that's okay, because it's still making accurate predictions. And the total amount of learning and data and everything associated with this is all proportional to the number of components in the teacher's representation. So this is a way of kind of like feeding the learner what it needs to know to learn something potentially very complex. Okay? So I don't know. I like that. I think that's cool. That is not it's not published work because other people didn't think it was that cool. But for a while, we struggled with the notion of, well, how do we move any of these ideas over into the reinforcement learning setting? And so I figured I couldn't really end this talk unless I solved that problem. So I've been working hard for the last week or so. And I have something that I think is really neat, which is a reinforcement learning sort of teacher-learner setup in this impact setting. So here's how this is going to go. The teacher is going to know a representation of the transition function in this case. So it has to teach the transition function to the learner so it knows how the world works. And we're going to assume that transition function is represented by a circuit, and I'm going to do just deterministic because I don't have all day. And anyway, I'm not going to handle the stochastic case. I think it's actually an easy generalization over what I'm going to say, but I haven't been through that yet. But it is definitely the case that these compact representations, like circuits to represent a transition function, there's a whole bunch of possibilities, but they're all essentially equivalent. So you can turn one into the other. So I think it's not particularly limiting to assume that the transition function is represented by a Boolean circuit, modulo stochasticity. But we can talk about that offline. All right. So then the learner is going to the teacher is going to pick a demonstration policy to collect some data about the environment. It's going to run that to collect data. And now the data is the states. And the states and the next states are all like binary vectors, essentially, right? They're not just a state tag. They're like a whole vector. And the teacher has the right, is allowed to hide confusing examples, but is then going to present that batch of information to the learner to learn about the transition function. And then it's going to signal the end of, it's going to do this a bunch of times, and then it's going to signal an end of a round of teaching, and then the whole sequence then repeats. All right. So at the end of each round, the learner's, just like before, is going to store what it has as a kind of intermediate representation that's now available in its kind of library of primitives. And it can build upon that. All right, so why can't we just take the impact approach and just apply it in this reinforcement learning setting? So there's a couple things that make this complicated. One is that the output, this next state, is a vector of bits and not just a single bit. So some of the tricks that we used in the supervised setting don't really apply here because, or at least the binary classification setting, don't apply here because you have a whole vector and there's lots of possible vectors. So the way that we're going to deal with that is for the teacher to really focus on teaching one output bit at a time. So that the output of the transition function is a bunch of bits, but really we're just trying to teach one of those bits right now. You don't have to pay a lot of attention to the other ones. The teacher's not allowed to tell the learner which bit, but supposedly it should be able to put together a data set so that what the learner learns is going to be that bit. All right. As I said, and the learner's job is just to make progress, not to learn that whole function all in one go. The output of next state is stochastic, as I said. I think that's easy to handle, but I haven't done it yet, so don't go out and like trade stocks on that yet. All right. All right, and so the thing that makes this really, I thought, interesting and brings a whole lot of ideas together is the notion that there can be ambiguity in what the learner needs to learn on any given run. In the impact setting, where there's just a fixed data distribution, it didn't matter. If there's ambiguity, it sort of has a different way of getting the same answer, and it knows that it can depend on that because the data distribution is very consistent. But here, as we have to deal with in reinforcement learning, as soon as you adopt a policy, that could change the distribution with which you're going to see examples, and it could very much disrupt some of those functions. They could just be wrong. And so we can't just like choose one. If there's multiple functions that explain the teacher's examples, the learner can't just choose one because it could be wrong. All right, so, right, and even if it's right now, it could be wrong later when the data distribution or the behavior changes. All right, so what are we going to do? And so I beat my head against this for a long time, and then I said, wait a second, this is what quick learning is for dealing with this lack of distributional information. And so here's the key ideas. The learner is going to avoid resolving ambiguities immediately. Like when there's multiple possibilities, it's not just going to commit to one. It's going to hold on to those multiple possibilities, just like we did with the divisibility case, right? We didn't commit. We predicted when we could predict, given what we knew, but we didn't commit because it's possible that one of the possibilities is wrong. So we're gonna hold on to that with the quick algorithm, or whatever the quick learner is for now. It's very simple. It's just going to be a like binary set of functions, like really simple 2-bit functions. So we can definitely quick learn in that space. All right. If ultimately there's no policy that disambiguates, like there's 2 possible explanations for one of the output bits, and the teacher can't find a way of saying which one is right, then it doesn't matter. There's no way to say which one is right. You might as well just choose either. So then you can commit. Then you can actually just choose one. And that's why the teacher has to signal, OK, I'm done teaching you with this particular bit. You can now just commit to whatever you're going to do. All right. So the teacher's going to collect data to teach a gate for one of the output bits. The learner is going to use a quick learning algorithm to figure out what that prediction should look like. And the next round, the teacher has to create a policy to disambiguate, to actually say, well, from what you've seen so far, these things are, well, it doesn't say this, but it's thinking, for what I've shown to this learner so far, these 2 possibilities are still active. So I need to act in the world in a way that separates those from each other. Okay? And again, that has to be possible, because if it's not possible, then it doesn't matter which one you pick. So if it matters, there has to be a policy that actually distinguishes them. All right, so that's going to pick that policy, the teacher's going to pick that policy, and we're just going to repeat until there's no more disambiguation possible. And then we can bound the number of rounds of this in all the standard things, a polynomial in the standard quantities. And when we're done, when all this is done, the learn transition function is going to be near optimal. So, like, I don't know, yay. So this seems good, because we can now, in the case of having a really, I don't know, sophisticated teacher, we can actually teach in the compact column. Like, this is the first thing that's polynomial in the compact column. We can actually get a guarantee on how accurately the learner's behavior is going to be in this setting. Okay? So you may have concerns. You should have concerns. I have concerns. I'm saying that the teacher has to know an awful lot. I'm saying that, and that's fair. The teacher does, I mean, it's a very powerful teacher. Not massively powerful, but like maybe too powerful. And there's probably heuristics that we, maybe as a community could develop to deal with that for some of this, incomplete information that the teacher might have, right? We're really depending on the teacher not just to have solved the problem, but to solve the problem with a very explicit kind of representation that can then be conveyed piecemeal. And I do think that a lot of teaching has that form, but this is maybe a little too granular, right? Like specifically, it needs to be and or gates, and so that seems maybe limiting. But I feel like I think we could get over that. All right, the teacher seems to need big-time computational power. So it has to be able to compute these teaching policies that, first of all, convey specific information about the transition function, but second of all, can do it in a way that disambiguates possible interpretations. And I don't know exactly how to do that. That feels like it could be computationally complex, but I don't know. Maybe we can come up with efficient approaches. It's a new question, so maybe we've got new answers. The whole moderation thing seems like a cheap trick. So the moderation thing is basically like this. Instead of just saying to the learner, I'm going to set up the world in a way that you can learn something really useful, we're not going to do that. We're actually going to set up the way that learning is going to be useful, and then I, the teacher, am going to hide some things from you so that you don't get confused. And I feel like not a lot of real life is like that. Like when we're teaching kids, we do hide a lot from them, but it's not at the level of individual muscle twitches, right? So this maybe needs to be generalized. I think there's other possibilities out there. Transfer learning, I think, is a really powerful thing where we don't have to necessarily get that granular, but we can actually take ideas that have been learned in other settings. Verbal descriptions are turning out to be really, really good. But I think really what I'm trying to get at here is just a proof of concept, the sort of idea that we could do this in this very narrow setting. Maybe we can generalize the setting and handle a broader set. The impact itself assumes a very weak kind of learner. Like it really is focused on all the possible complexity, all the different bits that it could be paying attention to. It's going to try to find pairs that do reasonable things, and that's maybe a little limiting. And I agree. Again, it's just want to kind of prove the concept that there's a lot of information that can be conveyed just in what examples that the learner gets to experience. All right, so that's really what I wanted to get at. Let me wrap up. I feel like in many ways the large language model community is reinventing all of AI, like agents and reasoning and decision making, and that's okay. New generations need to generate new knowledge in their own vernacular. But one of the things that really bothers me about it is a lot of the papers that I'm seeing, the guarantees, there are no guarantees. There's just a kind of a cross your fingers and hope kind of approach that says, well, look, I ran it on these things, and it was very, very consistent on these, except for the times that it wasn't, and it's fine. It's going to be fine. You'll be fine. We'll all be fine. We're not going to be fine. I feel like we need methods that work by design. It should work because it's designed to work, and not just because, well, if I prompt it the right way, it might do the right thing. All right, so that's sort of what I would like to push us towards a little bit. So, and in general, agents that can't be trusted are problematic. Right? This is not something that we as a community want to be hoisting off on the rest of the world. It's just trust us because we don't know what we're doing. Sometimes it seems fine, so you're good. I don't think that's okay. And maybe that's not the right way if we're just trying to understand intelligence, but I don't think that's exactly what this field is completely about. Some of it is we're also providing technology to the world, and that technology should be dependable. And so I think it's really important that we find a way to get this story back in. And Justin Timberlake might say, I'm bringing theory back. And that's a reference that probably no one gets, so never mind. But I did find an image. Justin Timberlake's a singer, he was in a group. Anyway, but there's a video of him, a music video of him singing. I'm bringing theory back was a Justin Timberlake. I'm bringing sexy back was a Justin Timberlake song. Well, I think it was just called Sexy Back. All right, so thank you. But there's a video of him speaking at the Pan-Asian Deep Learning Conference. This is a music video in a top 10 music song where he's actually like a character, not Bill Gates, the other guy. What? Steve Jobs, thank you. Yeah, that one. He's like a Steve Jobs character, and he's demoing this robot that comes out and does all these things that look a lot like Boston Dynamics things until they don't, because the robot becomes hypersexualized. Anyway, it's not a great video. I'm not suggesting you should watch this video. My point is that I reached the end of my talk. Thank you very much, everybody. This was great.